Okay, status register or SREG in IO register is another important register that we use in arithmetic operations because when we do any arithmetic calculations, the carry flag, the half carry, sign, overflow, zero flags are raised from here. Also, there's a flag for interrupts and there's a temporary bit that we can store over here. Now let's see how these flags can be generated based on some arithmetic operations. So for example, we want to add 0 hex 38 and 0 hex 2F. So what will happen? 0 hex 38, 0 hex 2F, when we add them. So if we write them in binary, this is 0011, 1000, and 0010 and 1111. Now, if we add these things together, 1110, there is 1 over here, 110, 1110. So this is going to be 0 hex 6, 7. Now, do we have carry? No, there's no carry. Do we have half carry? Yes, this is actually half carry. So transferring a carry from less significant 4 bits to higher, more significant 4 bits, it's a half carry. So it's 1. Is this, the answer is 0? No, it's not. So the output is going to be 0. So this is one of the examples. If we try another one, 9C and 64. So 9C is 1001, C is 110, and then 64 is 0110 and 0100. So when we add these together, as you can see, there's a half carry, carrying from 000011, carry 111, carry 1 over here, that's the half carry, and 110, 110, 110, 110, and also there's a carry. So carry is 1, half carry is 1, and as you see, the 8 bits of output is also 0, so 0 flag is also raised. So if we carry on with a different example with the subtraction, we have got A5, 1010, 0101, and 23, 0010 and 0011. Now, if you subtract them, that's 0. You have to borrow from here 2 minus 1, 1. This is 0. This is 0, 0, 1 minus 1, 0, 0, and 1 minus 0, it's 1. So there's no carry, there's no half carry, and there's no zeros. So it's not borrowing from anywhere, and there's no zero. There are no zeros in the output in total. So the output is not 0. If you try another one, so we have got 52 and 73, 0101, 0010, and 0111, 0011. So when we subtract them, we have to borrow from here 2 minus 1, 1. That has to borrow 2 minus 1, 1. It has to borrow it from here. So that means half carry has to be 1 as we are borrowing. Then this is going to be 1, 1, and this has to be borrowing from here, 2 minus 1, 1, and this is going to be 1 minus 1, 0, and this has to borrow from bit 8, so that means the carry also needs to be 1, and 0 has to be 0 as there are no, output is not 0. So another example, two same numbers, 9C and 9C, when you subtract them, no carries, no half carries, the output is just 0, so the 0 flag is raised. So as you can see, by using arithmetic operations, the status register is getting notified and raises a flag based on the result of the arithmetic operation. Now, why this is important? Now, we can use this status register or the flags in order to create a conditional statements. So in AVR, we have got branches like jump instructions using the flags. Okay, so branch if carry is 1, branch if carry is 0, branch equal, lower than, higher, branch equal, not equal. So based on the 0 flag, based on the negative flag, based on the overflow flags. So these branches, which are conditional statements, in the first state, we can check if they're equals to 1 or 0. If it is that, do something else, jump to somewhere else in the assembly program. Okay, so we can use these branches and we can jump to somewhere else, which we are going to do examples later on. Now, next thing that I want to cover in this chapter. Now, the assembler itself. So we are writing the code, which is a source file. Okay, we create that in the text editor, which is called a source file, and we saved it as .asm. Now, when we created that source file and the assembler that we are going to generate the machine code, it generates a object file which is going to be used by the simulator or emulator if you want to debug or verify the code, so track any changes or find out mistakes in there. And it also generates a map file, so it maps the labels that we have used in the code to actual machine code. And the list file is also generated by the assembler, again for debugging, and it shows the source and the binary code and the memory equations that are allocated for each instruction. And the hex file and EEPROM file, which is EEP, they are also generated by the assembler, which you need to use them to configure the flash program memory or EEPROM memory respectively. So from assembly to assembler to the matching language, we need an assembler which will generate those files so that the microcontroller that we are using can be programmed. And as you can see, the editor that we are using as a user, assembler program, and the files generated, and these two, hex file and EEPROM, are downloaded into the AVR. Now, when we talk about the structure of the assembly language, assembly program is a series of statements or lines, like we have done some examples, which are either assembly language instructions like add, LDI, or statement called directives. Now, instructions tells the CPU what to do, so these are written by the programmer. Directives are also written by the programmer, but it's actually instructions which give direction to the assembler, not to the CPU. So we tell the assembler like .eq name equals value. We are actually defining a universal constant over there, for example. So .eq sets something like a count, and when you are using a .eq directive, we have to be careful because .eq cannot reassign to another value when you are doing something else. Okay, and the alternative way of that, .set, which is another directive, which you can reassign it. So when you set it, then you can reset it to another number inside of your code. Now, .include is another assembly directive. So when you create your assembly program, you have to include a file, like the header file, which gives some special instructions and definitions for the AVR. So .include actually tells the assembler to start reading the assembling source code from a specified file. Okay, so it reads that file first. So for example, Mega 128 has got definition file, which defines most of these shortcuts and the special instructions over there. So we have to include that at the beginning so that we can use it. Now, you can see the example over here. The definition file includes some like equal definitions for like sreg, spl, sph, like we have mentioned in the IO registers, their addresses. So when we are using the program, we can just call those names rather than the addresses. But in order to do that, we have to, in the program, include that definition file so that we can call that, for example, SPL is defined over here. So in order to call that SPL, we have to include that include file or definition file into it. Now, .org is another important directive to the assembler. It actually changes the memory location. Okay, so when you set .org 0, it starts to write to the program memory address 0. Okay, so it changes the memory location within the code segment. So we can use that. Now, it can be after .csec or a data SRAM segment, DSEC, or an EEPROM segment, ESEC. Okay, so depending on what type of memory you are using over there, it changes the address of that or the memory location for that instruction. Now, if you don't set anything, the default location, it always starts with 0. But in SRAM, this is going to be in the following extended IO addresses. Okay, so as we are using generally the program memory, we normally set .org to 0 to start from the address 0, or if you want to write to somewhere else like this 7, you can set it to 7 and it will write the next instructions to address 7. Now, assembly language itself, which is this is an example over here, it consists of 4 fields. So when we look at it, here, like this one, which we have got a label, okay? Here is a label, okay? And then we have got a mnemonic, so a mnemonic is coming over here, and this is like the instructions, and then we have got the operand, and of course we need the comments. Okay, so this is a full straight line. As you can see, the label, a mnemonic, operand, and the comment. So this has to be the order for assembly language instruction, and we have to define all those 4 in order to derive an assembly instruction code. So label is optional. I mean, we don't need to define it all the time, but in mnemonic, which is the instruction, it has to be there. We have to tell the CPU what to do. And as you can see, we have got some directives to the assembler like .eq, .org, which can be used by the assembler. And these are LDI adds, STS, they are the commands for the CPU. So here is a label. It actually tells the jump instruction to where to jump. So if you put it somewhere here and you just say here, it will jump to there, not just here. Okay, so this is just to stay forever. So it actually allows the program to refer to a line of a code by name. So you should not have a long labels, just keep it short in order to have a simple jump instructions. Now, assembler map file, which is generated after the source code, like .equals_sum 300 is defined because over here we are setting the location for the sum. It's going to be in SRAM location 300, and we can say CSEC here it's going to be the instruction 9. Okay, so we are defining those so that we know where it is going to be staying forever. Now, the list file is the important part of the assembler. If you do remember in the chapter 1, we have done something like with the random instructions, which we were seeing the machine instruction and the address all together. Now, these machine instructions are related to this AVR assembly source code. Okay, so you can see how these instructions are implemented. We are going to see these in details, how they are decoded, and we can get those instructions from it. And instruction address, this is the program memory, which we are holding each instruction, and the address is given over here. And memory information is given in the assembler, so 22 bytes used in the flash memory, 0 bytes in the SRAM memory, data memory, and 0 bytes in the EEPROM. Okay, so we are just using the flash memory with 22 bytes, and these are all summarized in this table. Okay, so when we consider the flash memories, now the most important register in the AVR microcontroller is the program counter, this small logic block over here. So what does program counter is doing is, now the program counter is actually used by the CPU in order to point to an address of the next instruction. So when you think about it, program counter points to instruction 0, address 0. When this one is fetched and start to execute, program counter points to the next instruction. So when this one is executed, it starts to execute fetch and execute that one, and the program counter changes to 2, to 3, and so on, so forth. Now, what is important over here, the wider the program counter, the more memory locations a CPU can access. So that means that, for example, 14 bits program counter can access a maximum of 16K, because 2 to the power 14 is equivalent to 16K program memory locations. Now, in AVR microcontrollers, each flash memory location is 2 bytes wide, so 16 bits. So if we do an example, at Mega 32, whose flash is 32K bytes, at Mega 32, the flash is organized by 16K by 2. And the program counter is 14 bits wide. Now, if we have at Mega 64, this is going to change to 15-bit program counter. So we have got 2 to the power 15, 32K locations. And each location is containing 2 bytes. So in total, 64K bytes. Okay, so 16-bit program counter, it's going to be 64K, and 64K by 2 will be 128K bytes. Okay, so from 000 to FFFF. The program counter in the AVR family can go up to 22 bits wide. So this means that 22 bits, the AVR family can access to 0, 0, 0, 0, 0, 0 to 3, F, 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 a total of 4 million locations. Okay, so with 22 bits wide, program counter can reach to 4 million locations. Now, let's see how fetching an instruction using a program counter works. So as you can see, it's 16-bit wide for AVR Atmega 128. So you can see that we have got the program bus over here with 16 bits wide. Now, these are the instructions that are already written for us, or an assembly language over here. What it does is we have got hex 25 defined, 34 is defined, binary hex 31 is defined, and then we add 25 and 34, and we add 31 to the total of that. And then we define another constant, which is 11, and that's also going to be added to R16. And then we store the sum somewhere else and wait over here forever. And these instructions are given to the program memory. As you can see, the machine instructions are generated by their locations, and they are stored in the program memory. Now we have got these instructions in the program memory. Now the program counter points to the first instruction, which is 0, location at location 0. Then that is LDI R16 hex 25, that will be decoded. And then we have got instruction decoder has got E205 for this. And then that will be decoded. Then the program counter moves down so that it points to the first instruction, as you can see, which is 314. That will be decoded. While that one is decoding, program counter shows 2. And then when that one is decoded, we move down again, and the instruction decoder is showing 3, 2, 1, and the program counter is changed to third one, next one, and then it carries on like that. 0F01 points to the fourth one, then 0F02 points to the fifth one, and it goes like that until the end that all instructions are covered. So the program counter points to the next one all the time, and we have got 9300 STS instruction, and program counter shows instruction 8. And it executes that one and points to the 9, and then it just waits there and points to A, which is the next instruction. So this is how the program counter points to each of these instructions by going through one by one, and these are going to be fetched and executed. So another important thing over here, when we want to discuss about how these fetch and execute cycles are running, now if you consider, we have got two types of organization. One of them is multi-cycle organization. So how does this multi-cycle organization works? Now, these are the instructions waiting to be fetched, okay, by the CPU. Now, with the multi-cycle, you have to wait for each instruction to fetch and execute, and then it moves down to the done, and then the second one can move into the CPU. So as you can see, we fetch, we execute the first instruction, the second instruction is waiting over here. Then this is done, then the instruction 2 is going in, that will be fetched and execute, and then the next one, and then the next one. So multi-cycle operations or organizations, they are slow, okay? So they're not too fast because you have to wait one instruction to finish execution and then you can run the next. And this is how it goes for all of these instructions. Now, opposed to multi-cycle instruction, now new type of technologies or the microcontrollers, they are using pipelined organization. So what is pipelined organization? We have got the instructions again, okay? And when one of them is fetched, other one is waiting. Now, when one of them is executed, the next one will be fetched in. So we are not losing time over here. When this one is executed and done, the fetch one moves down to execution and new one will be fetched in. And then that will be executed and the new one will be fetched in and then the third one will be executed and so forth, so forth. So with the pipeline organization, you can have more faster and well-organized execution of the instructions. So few more things about the executions. Now, as these are all executed in the CPU, we might need to look at how we can speed up these processes. So in order to speed up the processes, we have to increase the clock frequency maybe, but we have to think about it because if you are having a faster clock, that means the dynamic power increases linearly, you have more power consumption, more heat, and also some static power dissipation as well. We can also increase the supply voltage and the frequency. So it's worse than that because increasing the supply, increasing the power more, as they're all defended with the CV square F at the beginning of the lecture, which we all told about it. So more power consumption, more heat, and more leakage power as well. Or you can change the architecture. So for example, instead of having a multi-cycle operation, you can have a pipeline or you can use a RISC architecture. RISC is a reduced instruction set computing, which we are going to talk about it next. Now, complex instruction set. So what is the difference is, this is a job interview question actually. You can put as many instructions as you can into the CPU with the complex instructions, but with the RISC instruction set, you can reduce the number of instructions and you use your facilities in more proper way. Now, there are some cons and pros about these RISC and CISC architectures, which we can say. So for example, the RISC architecture, they have got the fixed instruction sizes. So for example, AVR is also RISC architecture. When you have a fixed instruction sizes, you're actually going to make the coding and instruction easier. So generally in AVR, most of the instructions are either 2 or 4 bytes. But in CISC instructions like 8051, you can have 1 byte, 2 byte, 3 byte, or many different sizes of instructions, which becomes difficult to decode. And another feature over here, now the reduced number of simple instructions. So pros, it reduces the number of transistors that we are using, but the cons, writing an assembly, it's more difficult and you have to use more memory. So we have to be careful, there's a trade-off here. And feature 3 is you are limiting the addressing modes, which we are going to see in the following chapters. So hardwiring from instruction register to data path. So it's we have a advantage over there, but again, writing a code might be difficult as we are limited addressing modes we have got. So we have to be careful. Now, feature 4, which is the load store architecture, ALU operations are simple and are always between registers. That's what we have seen. Use simple dedicated load store instructions for register memory transfer, which would be less frequent than ALU operations. So RISC offers us this load store architecture so we can easily access to the registers that we want to do some arithmetic logical operations. And if you don't want to use it, you can move it to somewhere else with LDS and STS instructions. Now, feature 5, which we can add on it, the Harvard architecture, which we already mentioned in the first chapter. The CPU is sitting in between the code memory and the data memory. Now, that means CPU has a separate buses over there, and it can easily communicate with the opcodes and the operands. And if this is a code, so I can decode. If this is data, I can set it to data memory. Now, the advantage over there, they can go in and out at the same time to the CPU. But the disadvantage is the cost. As you are using more buses over there, it might be cost-wise and area-wise, might be more costly. So this is a typical RISC architecture. LDS, we are going to load data from hex 100 to the R20, and then we have to add R21 to R22. So we can fetch the first instruction, which is LDS, and then we do execution and we fetch the other one while we are executing the first one. And this is a typical RISC architecture operation. And this goes out, the other one is executed, and then other one will go out as well. So feature 6 about the RISC architecture. Common cases are fast operation between general purpose registers. This is really important as we are doing lots of operations in the CPU and arithmetic logic unit. You can directly get it from the general purpose register and use it. And the good thing, another important thing, 95% of the instructions are executed in one machine cycle. So it's quite fast for the RISC architecture. And the last feature, there is a high user accessible register count. So you have 32 registers, which will be enough to do a complex programming over there. You don't need to use stack or any kind of memory usages. And this will serve you as a fast and quick access to special registers. Okay, so that's all I want to say for this chapter. So if you want to review, we talked about the simple assembly instructions like LDI, add, subtract, increment, decrement, LDS, STS, in, out instructions. We have seen how assembly directives are used. So instructions are giving instructions or tells CPU what to do. Directives are telling assembler to what to do and so on. And we have seen how fetch and execute is done using multi-line organization and the pipeline organization, which is faster. We know now the RISC and CISC differences. And the AVR is a RISC architecture, and there are really good advantages, which is faster and more compact compared to the CISC architecture. Thank you.